All right. So we're talking about these two conjectures, Piccirillo conjecture, that two knots have homomorphic zero symmetries. That implies that the knots are concordant up to reversing orientation. And we said that Yasui found counterexamples. Just gotta remember how to spell. But these counterexamples do not have diffeomorphic zero traces. So that motivates an extension of this conjecture. That's called conjecture 2, which says that if you have diffeomorphic zero traces, then you concord. And I put diff here to remind you this is diffeomorphic.
I have a question actually already.
Yes.
So do you really need the diffeomorphism? I mean, are these zero traces often homeomorphic or always homeomorphic?
Let me talk about these up here.
Or just in general?
Probably
look at
not. Yeah, I think they're probably not.
Not even homeomorphic?
Oh, it means it's zero for knot traces.
Yeah.
If two knot traces are, yeah, if they're diffeomorphic, I mean, if they're homeomorphic, they might be diffeomorphic. But I'm not sure. Okay. Right. But anyway, this works for both, right?
Yeah, I think if zero symmetries are the same by Friedman, you know that the zero traces are homeomorphic at least.
Oh, I see.
Yeah.
Huh. Well, that brings us to the topic of the remainder of our seminar, which is this theorem. There are infinitely many counterexamples to conjecture 2. All right. And that's what we're going to be talking about over the next 4 weeks. It's how they prove this. And of course, this will also give counterexamples to the Piccirillo conjecture also, right? So you can kill 2 birds with 1 stone. All right, and so the way we're going to come up with these counterexamples is using this idea called patterns. So I'm going to try to, I only have one board here, so I'm going to try to start from the top and erase to the bottom slowly. Maybe this part too. So a pattern is just the embedding of a circle into embedding of a circle into a solid torus. Be consistent. All right, we're going to use B for the solid torus. And for this talk, we're going to assume that all our patterns are oriented and we're going to assume that it is not null homologous. All right. So here's an example. And unfortunately, colors do not go in this video very well. This is technically purple. It doesn't gonna matter for this one, I don't think. You guys can figure out what's going on. So there's a pattern. And now we're going to define some curves. We're going to find mu p, just to be a meridian of our pattern. So let's do the one at a time. All right, so let's just say mu p, so it's going like this. So mu p would look like that. And then we're going to define lambda v, just to be S1 cross a point, some point in the boundary of our disk. And we're going to orient our longitude to match our pattern. So in this picture, let's say that it is this curve right here in the middle. Can you see that? All right, good. And then we're going to define, let's now define mu v. It's going to be some point across the boundary of D2. It's going to be oriented such that this meridian, we want it to be a some positive multiple of the meridian of the knot. In the complement. And I'm going to use the N to denote the neighborhood. That looks kind of a little bad. You should write that. I'll use that notation to denote the neighborhood of the pattern. And that's because sometimes the pattern, this is not a braid, so sometimes it can turn around and go back. But we know it's no homologous, so it's going to have the meridian. It's going to be, if I look at, what I'm trying to say, if I look at one meridian, it's going to be some direction where there's more of going that direction than the other. And that's what we mean by a positive multiple. Right. So in this picture, that looks like, let's use orange. That looks like this. And finally, going to be lambda p. It's going to be a longitude of a pattern. And we're going to pick it so that we're going to pick it so that it's a ciphered longitude of using notation PU. That just means taking the pattern and filling inside a Hager torus, the standard unknotted torus. So that's what the pattern put into the unknot. So if I put the pattern inside an unknot, I get a knot in S3. It has some ciphered longitude, and that's what we want lambda p to be. And in this picture, I'm going to draw like the blackboard longitude here, which goes around. And in this picture, it's going to do this. There you go. The Lincoln number should be 0 with the pattern. So this is our setup. So now that we know what pattern is, we're going to find the dual of a pattern. Let's erase this much. I need the picture. We say that a pattern is dualizable and it has some dual P star. Maybe I should say pattern. Some dual pattern, I should say. Or if I should say, there is and I use this term in the paper. I use this term orientation preserving, which is a little confusing. We're going to go with that, talk about what that means in a bit. We have some orientation preserving homeomorphism from the complements of these patterns. Such that the following conditions are satisfied.
And V star just is a different solid torus, but it's still homeomorphic to the standard solid torus?
Yes.
Okay.
Yeah. All right, so what it does is it switches, let me draw a picture. So I'm gonna pick a nice, easy dualizable pattern. Like the trivial pattern. It's nice and dualizable. And so once you have your pattern, you have this neighborhood, which I'll just draw around it like this. And if I drill out that neighborhood, I get like two bounding components, which are both tori. And the idea is that this homeomorphism is going to switch the inside and the outside. That's why you go V's to P's. All right. And it's going to switch it in such a way that the longitudes get mapped to each other exactly, but the meridians get swapped. So let's draw the dual on the bottom. So this is P dual, which is also a knot. This is going to take, let's say this is the meridian like this. It's going to take this guy to this guy. Oh, my bad. Didn't switch it. To this guy. And this is going to be minus UV star. So here's what's tricky about this. In order to make this picture work, if you think about these as just little subsets of S3, inheriting the orientations, right? You want to actually orient this guy the opposite, the way you orient that guy. And if you do that, then that's what they mean by orientation preserving, right? Orientation preserving, where you assume that this orientation is opposite of that one. And this is upsetting for now, it's fine, but it's going to make a little more sense later on. All right, so any questions so far?
So does this homomorphism swaps like the inside boundary component with the outside boundary component?
Yes.
Okay. So it just turns it like inside out?
What it does, so this is the cross section, what it looks like, right?
Mm-hmm.
It does this. It just does exactly this. It's sort of
Okay.
does exactly like that.
That's how I think about it. Just think about it in general.
Yeah, but it's going to be, well, we're going to do a better picture later on. It's going to be easier to think about. By the way, duals are unique, and that follows pretty immediately from definition. And it's because if you have two duals, you can think of these guys as just complements of links in S3, where you just take your pattern and use a standard unknotted component, right? And you get a homomorphism of the link complement, which takes meridians to meridians. And so that tells you the dual is going to be unique. So any two things, wait a minute, let me be slower. If I had two different duals, I have some F going from P. Let me erase this part. I get an F going from, say, B minus neighborhood of P star to B minus neighborhood of P. But I also get another map. It's technically goes this way, but it's a homomorphism, so it doesn't matter the direction, right? We can think we're going either way. The point is we get another one to the other dual, say star star, which is bad notation. And this thing is a homomorphism which preserves the meridians, because the meridians get negated twice. That's what happens. So that's why we know that duals are unique. Any questions? All right. So how are we going to think about duals? So the way to think about duals in this paper is about thinking about putting your patterns inside S1 cross S2. So if you're given our pattern P, we get a embedding of our circle inside S1 cross S2. And we get it this way. So let's say our pattern was, let's go back to the little more complicated one. So we get this picture. So S1 plus S2, we're going to draw it like this. One small sphere and one big sphere. And it should look like this, I believe. And what you're really doing, all you're doing is just, so we got the outside boundary here is a torus. And all we're doing is doing filling on the outside torus so that that mu v bounds a disk, right? So just glue another solid tori onto this one so that this red curve bounds a disk, and you get that picture.
How do you decide the orientation? Makes sense.
The orientation of what?
On the right-hand side. I mean, how can you tell the arrows are going that way and not that way?
I mean, they're the same picture, right? You just exchange the outside and inside.
Okay.
I just, by convention, chose it this way. But, you know,
Okay.
you can always swap it, and it's the same picture.
Okay.
All right. So why is this helpful? So now I'm gonna draw a different picture with the knot to make it simple. So let's say you have your pattern here. We can recover our solid torus just by drilling out some neighborhood on the other side like this. Let's say we drilled out this neighborhood on the other side. If we drill this out, we'll get a solid torus again, right? And we now can identify what the longitude of the torus is now. This guy right here, this would be lambda v, except it's, of course, on the boundary component. Which means if our pattern is dualizable, like in this case it is, we know what the dual should be. It should be the whatever we get when we fill this guy in, and we get our dual pattern just sitting inside like this. That's our dual pattern. It's an interesting color. Can you see that color?
Can you say that again?
There we go. If we filled it into the solid torus, where I just take the core of the torus is going to end up being a dual pattern in this picture, right? Of course, in the knot, so like in this picture, this is not dualizable. But if it was, the dual would look like this if we embedded it in. I should put hats here.
Well, I mean, that doesn't convince me, but it's not, I'm confused.
All right, so why is that? Let's think about what's going on here. If we drilled out a neighborhood here, right? Lambda v is just going to be the longitude of this line here, right? Literally, the longitude of this line here is this lambda v. And the meridian of this line here is just going to be whatever we had for the negative of whatever we have for the meridian here, right? So let me draw in the meridian. This is mu p. You know, you can isotope it over here. And this is going to be minus mu p star, right?
But I don't understand which solid torus you're drilling out now, actually.
So we're drilling out both, right? So it's kind of hard to see now because I did both already. So first, we're going to drill out just this one, and we get a solid torus, right? And then you drill out a neighborhood of your pattern, right? And once you drill out both of them, then you can see the identification of mu p with minus mu p star, and lambda v is, of course, just lambda p star.
Well, not always, right? Like, not in this case you drew above.
No, it is. Because lambda v is not going to be twisted at all, right? So this right here is lambda v, right? Even in this picture. And if I drill, and this is also, if I drill this out, this is also lambda p star, I should say, right?
But p star, I thought you said p star doesn't exist here.
It doesn't. Don't worry about that part. I'm just saying if it did, it would be. We're gonna talk about why this doesn't exist. But if it did exist, it would be exactly like this, right?
Okay.
Wait, this confused me because, like, looking at this picture, it makes me think that, like, every pattern has a dual, and that dual is just like
it looks like it, right?
unbonded.
But the reason why it doesn't is that if I drilled out this, if I drill out a neighborhood of this guy here, I won't actually get a pattern. I won't get a solid torus. And that's what breaks. I get a space with the torus boundary component, but it's not a solid torus. So that's what actually breaks that it's not a pattern.
Okay. Oh, so the homeomorphism, we filled like this land the V in.
Right, right,
And then we glue out a neighborhood of P hat, I guess.
right,
Cut that out. And then that should be homomorphic to S1 cross D2. Right?
right,
Once
right.
you okay.
Right. But in this case, it isn't.
Yeah, I see.
And that's what goes wrong.
Cool. Okay.
In this case, it is. And that's why it's correct. Right. Now, what's nice about this picture is that, like we said before, V, where this is just S1 cross S2, where we remove a neighborhood of P star hat, right? We move out the dual side and you get our V, right? And V star is just going to be the same thing where we just drill out the pattern. And now the identification of the two complements is real easy because we now get that this guy is just going to be in this picture literally the same as this guy, which is just S1 cross S2, where you remove both neighborhoods. So in this picture, you drill out both neighborhoods and you get both complements, right? But if you want to view it the right way, you need to, we're swapping what the outside guy and the inside guy. And that's where this orientation reversing thing comes from. But in this picture, you don't have to worry about the orientation stuff because it's literally just the way it looks like in S1 cross S2. The orientation that you inherit from S1 cross S2 is orientation that we're going to use, right? So that's why that's what they mean by orientation preserving. They mean this identity map between the two that you get from this picture. So this is the hardest part of the entire talk, by the way. So if you can get this, then down here should be smooth sailing. So any questions for right now? So there's some benefits of working in S1 cross S2. Then we get this nice property. Pattern is dualizable if and only if that pattern in S1 cross S2 is isotopic to, I'll say, lambda V hat. So the idea is that, I'll draw a fresh picture. So if we have some more complicated pattern, like let's say this one, ooh, something weird here. There we go. That's still weird. There it is. Okay, so this pattern, it turns out, is isotopic to this guy. So this pattern is dualizable. And that's what goes wrong in this picture, right? If I looked at this picture, this guy is not isotopic to just this.
Probably the paper said this, but does this give you something about the algebraic
Yes.
winding number?
Yes, I'm going to write that next. The proof is not too complicated, but I'm going to skip over it for now. But you want to talk about it later, I wouldn't mind talking about it. This gives us some nice corollaries, as Hannah was talking about. The first, it says that if P is dualizable, then this pattern has algebraic intersection number 1. Not intersection number, winding number 1. Which is kind of intersection number anyway, right? And that's because the intersection, the winding number of lambda v hat is going to be 1, right? So if I think of, if I want to figure out, you know, what the winding number of this guy is, I just take like a nice sphere in here and figure out what its intersection with that guy is. And since this guy is going to be 1, this guy has to also be 1 if we isotopic. And secondly, if P has geometric number, winding number 1, then we have that P is dualizable. And the dual is just itself. And so let's do a picture of this situation real quick. So let's have a pattern that's like, I'm going to do it this way. I do this every time. There we go. Let's say we have this pattern. The point is that we can isotope this just by taking our sphere here and just sort of dragging it along the knot until you get to the other side, right? And so we get this picture. Right. And finally, a property that we're not going to use today, but it's good to know, is that if P has algebraic intersection, algebraic winding number, one, then we have a necessary and sufficient condition in this case for when P is dualizable. And that's if and only if, this one I'll never even remember. It's if mu P is in a normal subgroup generated by mu V when I'm looking at pi 1 of the complement. I'm out of the room. There we go. All right. So let's actually find a dual. You want to do that? All right. We're going to find the dual of J. Got in that. And J is going to look like this. All right. So the first thing we're going to do is draw our picture in S1 cross S2. And for the sake of space, I'm going to not draw the outside sphere. I'm just going to draw the inside one.
Is this the one in the paper?
This is the one in the paper.
Okay, I'm struggling to copy it, but I can just look at the paper.
Yeah, yeah. There we go. All right. And to keep things straight, I want to keep track of the, let me orient this. Let's orient this a little bit. All right. I'm going to keep track of the cipher longitude. There's a little bit of things we got to do here. We got to worry about, we want to make sure that this longitude is a cipher longitude, right? And there's a formula, which I'm not going to explain, I'll just write down. If you want to figure out, so this, when we go along this guy here, we call this like a blackboard framing, if you remember? And this formula says that if I want to figure out what the cipher framing of a curve is, then I just take the rise and add it to the blackboard framing. And we want the cipher framing to be zero. I should say the inside the space framing, right? So we need to figure out what the ride is, and you can compute it. These are all plus, and these three are minus. So you compute it, you get +3, which means this blackboard framing better be -3. So what we need to do is somewhere over here, let's say right here, I put a box that twists this up -3 times. So now this is our picture of J along with lambda P. So this guy is lambda P. and this guy is J. And what we also want in this picture is this guy, which is lambda V. And we're not gonna worry about, we're not gonna have to keep track of the framing on this side. Because they'll just work itself off, it'll work itself out if we isotope it correctly. All right. So now what we want to do is just isotope this picture until we get something where we get the dual on this side and the regular guy on the other. All right. So what's the first thing we're going to do? The first thing we're going to do is take this part right here and sort of pull it around to the front so it's no longer hooked onto this. If we do that, we get this picture. There we go. It should come out over here. All right, there we go. Good. All right. Now what we want to do is take this part right here, and we just want to pull this through all the way into like the outside surface that's over here somewhere, through to the other side. If we do that correctly, we should get this. So you can see we just took this green part and just kind of pulled it through. All right, now here comes the real fun part. I'm gonna erase the bottom picture now. So I'm gonna take this green part, and I'm going to isotope it along so I can flip it to the other side. So on this side, we just kind of do like this. Let me draw this a little bit neater. And I got to do the same thing over here, right, to match it. All right. And now we're going to take our sphere and we're going to isotope it all the way through. Do it right here. So this side is easy. Now the other side, we get this picture. I kind of ran out of space down here, but this is just going to come back down and come back over here. That's the idea. That's just this part right here. It's going to be down here. So you see, all we did is just move this all the way through here, right? Same thing. Okay.
Can you describe, I don't really understand how to visualize that. So you think of pushing this sphere along the blue and red curve?
Yeah, just push along the blue and red curve, right? You just isotope it along the blue and red curve.
Oh, okay.
It'll drag the greens, and it drag the green strands along with it, right?
Okay, I'll try to draw that.
How's the green look? Do I need to use a different color?
Green is good.
Okay. All right. So now, I'm going to take this part right here, these three strands, and I'm going to drag these down a bit. I'm going to take this part right here and push it up. I'm going to draw the picture first, and then probably make more sense after that. Actually, I want to give myself more space. Yeah, this is better. Mhm. There we go. All right. So I just take this part right here and I drag it up through there. Okay. Now this is nice. So if I look right here, what I get, well, let me do something real quick. I'm gonna take this strand here that goes underneath like this, and I'm gonna move it up some. So I'm gonna take this strand and move it out here so it's out of the way. All right. And now it's really clear that right in this area, I have a different color. In this area, I have canceling twist. One going this way, then one going the opposite way. And that makes us happy because now we can turn it into this picture. All right. This is much better. And now there's one more tricky part. It's right here on the end. I want to isotope where this guy goes to the boundary a little bit. I want it to go over this first strand and then under this guy, like that. In order to make that work, I got to do the same thing over here. So I need to go over this strand and then under that guy. So it should look like this, right? So if you could take this part and glue it over here, you see I didn't change anything. All right. Now let's see if we can finish this up. I'm going to take this guy, which goes completely over. This guy right here goes completely over. I can change it to like this. And this guy, which goes underneath here, I'm going to flatten this out a little bit too. By the way, if you've ever wondered what it's like to read with Cameron, this is kind of how it feels a lot of times. So I'll take this guy, which goes under here, and I'm going to move it under like this. Actually, I won't go down like this. So instead of going under here, I'm going to go under over here. I'm just pulling it across. And then, see what we can do now. I can take this guy, which goes under these two, over these two, then under these two, and then over here. I'm going to change it so it goes down like this, and under like this, and then over right here. And then finally, I can take this guy, now that I put it down, now it just goes under these two, which means I can just bring it under everything up here. So under, and come back around there. All right. Right here in the middle of the picture, have this sort of loop-de-loop picture thing by going on right here. And I want to shift this down some. Yeah, let's just do it like this. I want to take this thing right here and I want to change it to look like this. So I'm taking this part and I'm shifting it down. All right. I'm pretty sure you guys didn't follow that, but there's a video. You can look at it later and think about it, right? The rest of it should be a little bit easier. Now we can unkink this part. And now that I've done that, I'm going to redraw this picture a little bit nicer. Of course, we still got our framing over here, right? That's still there. This is still here. Now this side, we have this picture. I'm going to go ahead and remove this Vitamin 2 move here, by the way. So we should just have this. There needs to be something over here. Wait, I confused myself. There we go. All right. All right, I think we have this picture. There we go. There's one last thing we're going to do here is we're going to introduce our Vitamin 2 move here, like this. And this is nice. So if we look at this side of the picture, I just get J. This is what we started with. And if we look at this side of the picture, if I look really closely, this is just a -1 twist on these 3 strands. So we end up in the end with this picture.
Could we have gotten this if we do this like rotation that they talk about in the picture before to unkink the the strand on the right-hand side before we start to push through?
Yes.
I mean, it's hard for me to visualize which rotation it would be, but like a rotation of the like the inner sphere by 360 degrees would unkink this loop we had before on the right hand side.
Yeah.
Okay.
You could have done that, yeah. But I'm just gonna draw this. I'm gonna move these to the other side and just draw that. All right, there we go. So I'm going to introduce a notation for this.
Wait, sorry, so if you just do this sphere pushing through stuff, then you never have to talk about this rotation that they introduce in the paper, right? Because you know that, like, if you try to push these -3s to the other side, they'll just come out as -3s. Is that the idea?
Right.
Okay.
So so if I'm given a pattern P, which remember is embedding into the solid torus, we're just going to define tau n of P which is just going to be the pattern obtained by doing n many Dane twists, right? On a solid torus. So with this notation, we now can say that J dual is tau -4 J. This is J along with -4 Dane twists. And this is an important fact for later on. It's going to come up again. And now to end off, I'm going to list a few more propositions. So first of all, why do we even care, right? Well, we care because of this proposition. If P is dualizable, then we know that if I do zero surgeries, when I put the pattern inside unknot, I get I get the same thing. And this is true. I'm not gonna do the whole proofs. The idea is that if I do zero surgery on a pattern, well, what we start with is B minus neighborhood of the pattern. And we're going to glue into it S1 cross D2 via the longitude of the pattern, and also glue to it an S1 cross D2 via the longitude of the outside torus. And remember, because when you have a dual, you have a homeomorphism from B minus neighborhood of P to B star minus neighborhood of P star, which takes this longitude to the other longitudes. So you're going to get the same Dane feelings. You can extend those this homeomorphism to the geosurgeries. Some other things that might be useful. Again, if you have some pattern with a dual, then we get that the dual of tau to the n is just going to be tau to the minus n of the dual. And finally, here we are. I'm going to go ahead and do this proposition. We can relate the in-fold surgeries on these patterns. So if you have a dual, we can actually figure out the in-fold surgery on a pattern just by taking in-fold surgery on so many Dane twists of the dual pattern. And there's finally a little bit of notation that I want to define for later. So eventually we want to, so this is talking about zero surgeries, right? We want to eventually talk about zero traces. So we want to take this homeomorphism and extend it to a different morphism on the zero trace. And in order to do that, there's this one concept which I'm just going to define here, and then that's going to be in, which is called the, I don't know what it's called. I was going to write the notation. So given P, we're going to define a pattern P bar. And here's how we're going to define it. Consider the map iota from S1 to S1, which is given by, you take your circle and you just reflect it amongst the sort of horizontal axis, right? This is going to be an orientation reversing map. And P bar is just going to be the map we get from, you start with S1, you're going to map to S1 by iota, and then we can do P to get inside a solid torus, and then we're going to map to the solid torus again by doing iota, cross, and do the identity on the disk part. So both of these maps are going to be orientation reversing. So what we're doing is reversing the orientation on S1 and reversing the orientation on the solid torus. So this gives us a different pattern. And our last proposition says that the dual plays with this with bar very well. P bar dual is P dual bar. There we go. All right, so that's it for dualizable patterns. And next week, we're going to start trying to extend this idea to zero traces.